Thank you. And as Olafur said, I'm going to cover two topics. First of them is going to be verification of the forecasts. So once you have your model set up and you think you chose the right options, now it's going to be how to verify if the quality of your forecast is the one that you are supposed to have. And the second is how can you approach the topic of point forecast, which is something that you would want to have once you have the area forecast, because you have your points of interest that you want to make forecast for, and how to tune them or how to make them as good as possible. First, I'm going to introduce you to the topic of forecast verification and tell you how can we match the forecasts with observations, in what way can we make the point forecast and match it with observation. Then what are the measures to see what is the amount of the error on the forecast. I'm going to speak a little bit on representativeness error, and in the end I'm going to cover the topic of improving the point forecasts. What is verification? It's just the evaluation of the quality of the forecast. The easiest way we can make the verification is to compare the predicted values with some reference values. Whoops. And they answer a very important question. Can our model be trusted? Why do we want to verify? We want to see, as I said, if the model can be trusted. We want to see if the version of the model that we have improved the forecast or not, since when you are working with models like WRF, you usually want to work with the most recent version of the model, and you want to verify in what sense did it improve your forecast and did it improve it. Which options to parameterization to use. So as the discussion that we just have, we want to know how to assess if the options for the cumulus or other parameterizations are the proper ones, as well as is our resolution good, and is our domain size okay, or is it too small, or should it be moved a little bit to a side? And finally, what accuracy can we expect while we go operationally? When a forecast is good, imagine, there is some mismatch of my slides and the screen here. I'm sorry for that, but I think we can cope.
How much minus? Just try to reduce
the size. Or I can just. I will try with this, and if I have further problems, I will then try to do something with it. But you can still see what I want to say. So imagine that you have a forecast and observation, and you see that there is a little bit of mismatch. Your observation is here, your forecast is here. You forecasted for a correct time, but in the wrong place. And imagine that you are forecasting for a watershed, and you forecast rain, and your rain happens outside of it. and you're in your forecast, and then you observe it on your watershed. So it's a wrong forecast. This forecast didn't bring the information that we wanted. On the other hand, imagine that you are planning a route for a flight, or for a plane, for a flight, or for a ship, or for moving from one point to another. Then it's enough that you know that the rain is going to happen at this time, and from this point of view, your forecast is good because it predicted rain where it and the rain did happen.
So basically you have the same forecast, but for one customer the forecast was very bad, but for another customer it was very good. So the quality of the forecast can also depend on the usage of the forecast.
Okay, you can have different types of observations or another references that you can use to compare your forecasts to. The most obvious seem to be observations, but then we have to decide which kind of observations do we want to use. What is the quality of the observation? Are we sure about the quality? Are we certain about it? Do we know that our measurement devices work okay? And do we have enough of the observation? Do we have a continuous time series of the observations, or do we have some breaks, or do we have the observations for the same time that we have done our forecasts? As alternative, we can use some model products such as analysis or reanalysis. There you are also working on an area of a grid, but this brings different problems, such as that when your analysis is coming from the same model as your forecast, then some of the events can be the same just because it's the same model. So there is not real verification of the truth, because some events have been created in the same way because the analysis is just it's not the same as observations. Also, there is a problem of resolution, so we are not always having the same resolution of the analysis as the resolution of the forecast. And it's also important to know about what is your temporal resolution, because you have some of the events that you want to assess if they were forecast well, such as sea breeze or some short time events. They just are outside of your reanalysis or analysis, since it's 6 hours most of the time. There is another way of comparing, which is called reference forecast. Then you use some sort of either naive forecast, meaning that some value is going to be constant during all the time, or some value is going to be the same as it was the previous hour or day, or you compare to some general model result. So this is different type of comparison. Now I touch a little bit the problem of point forecasts, which is the same as choosing the best match of forecasts and observations. Basically, if you have a grid which is a part of your model output, then you have longitudes and latitudes of these corner points in a box, and you have an observation that is somewhere here. How do you know what to compare with this observation. For example, you can think of taking just the nearest grid point, but then your forecast has been 0, observation is 10. Is it a good result or is it not? Alternatively, you can try to interpolate. You can have many ways of interpolating. In here, in this example, there is just an average of all the values. So all of these values of these grid points have a weight of 1, and then the average is 15, and your observation is 10. So the error is, in theory, it's reduced. Another way, I think the most common of matching a forecast with observation is bilinear interpolation, which is defined as a weighted average of the 4 points around your observation, and it's defined so that this point has a weight that is equal to this area. So this dimension times this, and the resulting equation is just the sum of this weight, a value for a point times weight. What are the measures of the error that we can have in our verification? It depends on what is the nature of the variable that we are verifying. For example, the most common are the continuous series. So this is wind speed, our data for wind speed, temperature, humidity, etc. But on the other hand, you can have dichotomous values such as did an event appear, did a precipitation happen or did it not, did the thunderstorm happen or did it not. You can also have some multi-category, so some types of precipitation or some thresholds that you have on the amount of some value. I'm going to present a couple of simple measures, how can you measure the continuous values, since this is what you will deal with most of the time. So the most popular measure of easily estimating the error is the mean absolute error. So this is just the average of absolute errors. So you have average of the absolute of the error. So the difference between the forecast value and the observed value. Then another measure is the mean square error or mean squared error, and the root of it. Mean square error is now I will better have the slides, the equations. I'm sorry. Yeah, that's what I'm doing, or I know what I do. I do this. I just use this PDF and almost there. No, this is not the one. Okay. No. Okay, it will be like that.
Go like this.
Go to the Zoom after.
Yeah.
Go back full screen.
No, full screen is.
Yeah, then you go to the Zoom and yeah, now go back to the Zoom at the top. Arrow. Fix height. Fix height. Only width.
No, it's because it understands that there is a different resolution.
70%.
So I need to, so I need to take, I don't know. I think this is enough. Okay, so back to the error. So the mean square error is again the average over your time series of your forecast minus your observation squared. So this has the dimension of the square of your forecast or observation. So you have sort of different units of it, or yeah. So the main property of it is that it penalizes the large error. So if you have some outliers, then you will have a very large error because it squares everything. So the higher the error, the higher the error on a particular pair of observation and forecast, the higher the total error would be. Root mean square error is just the square root of the above, so it has the same dimensions as forecast and observations, and the mean absolute error. A different way to compare forecast to observation is to calculate the correlation between your time series of forecasts and your time series of observation. This will not really give you the information what is the relation about them, what is the linear relation, but you will find any linear association. So sometimes you can have some sort of scaling that happens for some reason that you can easily spot out, finding out the correlation between your time series. Another way you can use to produce your errors is to present them on a time series. Then you can have a picture of what periods of your observation have been forecast well and what periods of your observation had problems. We usually use two of them. One of them is just the forecast error, so the series of error between the forecast values and the observed values, and running root mean square error. This is a picture of it showing the time series of a forecast in a blue line and time series of the measurement or observation in a black line. And this is the forecast error, the green line, so it's just the absolute error. You can see where there was overestimation and where there was underestimation. And the running root mean square error means that for a particular point you have a root mean square error calculated over a time series of the length of your window. In this case there is 6-hour window, so there is the value for this point is the root mean square error of the last 6 hours. Now a few words on the representativeness error, which is a sort of error of completely different origin that we have to be aware of. This is an error coming from the mismatch between the scales that your area forecast and your observation have, such as in your area forecast, your value for each grid point is in fact an average on an area of the size of your resolution. So the value for the point could be true for any of the locations in the area of the size of your 3 kilometers or whatever your resolution is. But your observation is made in a point. So if you imagine that you have like a full knowledge about the wind field in your grid box and your observation is at a certain point, then it will never be in practice equal than an average of it, which means that this is something that you cannot compensate for, and this is something that you have to have in mind, that you will always have a mismatch between your observation and your forecast. Oliver, maybe you have some examples. What is the size of the error? Do you have any experience? Have you tried to estimate it?
We have thought of it a lot, but it's difficult to get a true estimate of it. One way is to get an idea through doing a dynamic downscaling, and that way you can actually try to get an idea of the maximum quality of your forecast for a given model setup. But to get your hands on the representativeness error, you would need, you might try to set up, say within a 1,000 by 1,000 meters grid, you might try to set up 100 temperature gauges. So just to get an idea of, one temperature says 5 degrees, but within this 1,000 by 1,000, there are others saying 4.9, 4.7, 5.2, 5.3, just to get an idea of the temperature. But if you want to do it with wind speed, transportation can be very tricky because transportation can vary so much over such a limited area. But one way to do it might be like to set up an array of rain gauges for a given area for a given time. But it would require a intensive observation over a given period. So it's
an unknown. So it's an unknown.
Definitely very, very case dependent.
yes.
So
Because this will, in a way, give us information how much can we still improve. But
in a way, and also what to expect, because especially with precipitation, you can have a bucket here, but if you go 500 meters to the west, or on top of the mountain ridge that's 300 meters away, you have a completely different precipitation, either much more or much less. But I think, again, this is something that comes with time and experiences. When you have run your model for a certain amount of time for this region, you start to get a feeling for, and also if you know the region well, you know that there is a rain shadow in this part of the mountain, in this wind direction, or the other. You also, it's a combination of experimenting with the models and local knowledge. You should also keep in mind that local knowledge on the local weather, that's what you know. And just because you have a new good model does not mean that your local knowledge is worthless. It gets even more important to keep in mind your local knowledge to try to pinpoint the problems the model might have and apply that knowledge to improving the model performance.
So, in a sense, it also depends on the heterogeneity of the surface, isn't it?
Yes. But this is something to definitely keep in mind, that there is this thing that's called representativeness error, and at times it can be very difficult to get your hands on. So it's location dependent and time dependent.
It would be very nice to get some feedback on what the big errors are in your forecasts. When do they come and what kind of weather give you the big errors that are important?
Okay. Few words on point forecasts. When you have your area forecast, you come to the moment that you want to create. You have your list of points of interest, and you want to create the forecast just for them. You have your airports, you have your city centers, you have your small islands, or any other type of point of interest, and you want to produce a point forecast for it. This is similar topic than I just covered when trying to compare with the observation, but now your purpose is to provide some output out of your model to your clients or to your audience. How to get a point forecast for a grid? Again, we can take the closest point. You can take all the surrounding points. You can think of different ways of combining points. You can think beyond that and take all the 4 times 4, so 16 grid points. You have then decide what weights do you give to them. You can weigh them by bilinear interpolation. You can weigh them by the distance that they have. But you have to start considering what is the neighborhood of your target point, because it happens very often, as in the previous pictures, that the closest point is not really representative for our target point. Just because the closest grid point is on a sea and your observation is on the land, or you have some sudden change of a terrain, so your closest point is at completely different regime and conditions than the point that you want to forecast. So you have to think of how can you develop different ways of creating a point forecast so that you take all those issues into account. So what you should do is basically create your weights for your weighted average of your neighboring points, not based on the distance to the point, but based to the importance of predicting a weather in this certain point of interest. So the solution that we implemented is to identify the best combination of the nearby grid points to maximize the mean square error between the forecast value and the observations that we have. So we used our data on observations and our data on historical forecast to create a multiple linear regression over the observation with the values from the grid forecast to obtain the optimal set of weights for of the neighboring points. This is a little illustration of it. We decide that we want to use at maximum of n points. In this case, n equals 6. So you go beyond the bilinear interpolation, you look further. And in this case, your observation is here, and it turns out that it's not those 4 points that are the most important. Here you can see that, okay, this point gets the highest weight, but then it's this point and this point, but then it's these points that are more important than the point that is still in a grid that contains your observation. Which means that you can also have choice of points that are on the side of your grid compared to your reference point because of the terrain, because of other conditions that your specific model has, or model result has.
Are you suggesting that the people here, they define the coefficients by minimizing the mean absolute error or the root mean square?
Yeah, this is basically the idea behind a linear regression.
Yeah.
Like linear regression is working as minimizing the root mean square error and over the set of independent variables.
And this method is actually included in the forecasting suite.
So it's the linear regression method that decides how important are particular grid points, and the weights produced by linear regression we use to produce a point forecast as a weighted average of values at the points, as in a previous slide. So this is how we create a point forecast. So the value of the point forecast at this point, at each time, would be the forecast for this grid point or this grid point plus times this plus this grid point times this plus this grid point times this, and so on. This is some results that we got. This is performed in Iceland for the 86 observational sites for wind speed and for temperature. And this is an improvement compared to bilinear interpolation method, which is the most common and usually used method in creating point forecast. So you can see that you have some really well performing stations, even up to 60% of improvement or 50% of improvement. However, there are some stations that, by stations I just mean observation points, because we were using this observation from this station to create our weights and then our point forecast. So it's just the naming. But let's say that target points. So for some of them, there's a good performance. For some of them, it's a good performance on temperature and bad performance on wind, because
It's not good about it. It's the relative improvements of the forecast. So you
yeah, like the performance of the
might have
improvement.
where the temperature forecast is in general very good, and you get very limited improvements, relative improvements through the linear regression, but you might be improving the wind forecast a lot, and vice versa. So it's the relative improvement of the forecast using the linear regression method. So
At what resolution is this?
3 kilometers.
Do you want to comment something else on the previous slide? Do you want to comment something additional to the previous slide? Okay, yeah, this is another visualization of this time root mean square error of our forecast compared to bilinear in interpolation. So the dashed line are bilinear, the solid line are our best linear regression weights, and you can again see wind speed is blue lines, temperature is the red lines. You can now see the error, however you cannot really see the values. I think it's 3 and 4. I don't remember.
Yeah, in general, the temperature forecast is improved by at least half a degree, and the wind speed is improved by up to 2 meters per second, and this 1 meter per second. So these are absolute values as opposed to the relative values of the slide before.
So this is a list of the ideas that we have to improve this method further. We think it different ways. First of all, we can think of different weather conditions, and is the set of weights always the same for different weather conditions? Because sometimes you can have different grid points or different points can have different influence on your point of interest in different seasons, for example, because you have, for example, prevailing winds from this or other direction. The same as with different weather conditions, like in the boundary layer you have different stability at night and in the afternoon. So this is one of the direction that we want to go, to extend our solution for this linear regression weights with customization in terms of different weather. And another is some composed, more intelligent methods beyond the linear regression. We can think not only statistical, but incorporating some other ways of calculating this. Another way is to, instead of forecast data, use dynamical downscale data to produce our data for our point forecasts and for our weights, instead of the forecast data, which is always with more error than the actual data at the moment of the time. So that's it from my side. Thank you, and if you have any questions, then we can answer them.